All right, so now we're in a position where we can actually use group theory and these character tables to actually do something. Specifically, what we want to focus on in this video is thinking about how do we understand vibrational motions in molecules according to their symmetry, their point group, and all these facets that we've involved so far. So yeah, during this, don't forget, we have all these different components. We have our symmetry levels, we have our representation, or the symmetry of those representations, we have the actual representations, we have the symmetry functions. We saw that these tell us about all sorts of properties, like the d orbitals or the p orbitals. But there is a lot more to this, and we're going to see how we use it to understand how things now move in three-dimensional space. First thing we need to define is the concept of degrees of freedom, which is really just how many ways can this molecule actually move overall. So let's start with a simple example here where I have a diatomic. This could be something simple like N2, but we recognize for any molecule that's a diatomic, I've got 2 atoms, and on each of these atoms, it could move in any of the 3 Cartesian coordinates. So that's the first thing we could think about is moving one atom. It can move in 3 total directions. But what happens when now we have this bond that is connecting us here and keeping these 2 together? So what could happen? Let's take a look at that. So we could make the assumption that, hey, both molecules move in the same direction together. So example, maybe they're both moving in the z-axis, or maybe they're both moving in the x-axis, or both in the y-axis. Doesn't really matter, but we could think about this as the whole molecule being moved. This is what we refer to as a translation of the molecule. So if we look at this, since there are 3 Cartesian axes for each atom, there's a total of 3 ways this molecule can translate, or 3 translational degrees of freedom. What would happen, though, if they weren't moving in the same direction? For example, maybe one went up in the z direction, one went down in the z direction. Since they're tethered to this bond here, we notice that they're going to be moving around the center of mass, and this would start making a rotational motion. So in the case of this, we could look at all the different ways that we could rotate the molecule, and here I have drawn 2 different ways that we could think about rotating this. Technically, there is a third rotation if you really want to get spicy here, but it doesn't actually mean anything in terms of symmetry. So the other rotation we would recognize is the one that is around the bond axis. So that's not one that is going to be all that meaningful for us, because no matter how we turn it, it's always going to be the same. It's like it didn't move in the first place. So in essence, that's not a degree of freedom. So when I think about the terms of rotational degrees of freedom, I would just have these 2 motions here. A final way that this molecule, this diatomic, could move is if we see that they are moving in opposition to each other. Since they're connected with a bond, remember, think about a bond as a little bit of a spring, so it's going to stretch out and then come right back to its initial position. This is what we'd recognize as a vibration. So when we think about all the different aspects of how a molecule can move, this is how we're going to break it down. We have translations. There will always be 3 ways we can translate a molecule. When we think about rotations, there are either going to be 2 or 3 ways that we can rotate a molecule. We'll see a third when we get to something with a little less symmetry than this infinite principal axis. The rest of the molecules of all the other combinations of our Cartesian axis would be described as vibrations. So we're going to need to figure out how we can actually find out how many of these we actually have, because this is going to depend on the size of the molecule. So how do we do this? We're going to assign XYZ coordinates to every atom in our molecule, and we're always going to have the z-axis parallel to the principal axis. So same thing we've always done. Oftentimes that z-axis is going to be the one that points up, but it's the one where our principal rotation is found. Just doing some simple math, we recognize that each atom can move in 3 directions. So we've got 3 directions it can move times the number of atoms in a molecule. This is our total degrees of freedom for that molecule. And again, degrees of freedom just means how can we translate it, rotate it, or see a vibration of the molecule. Now, all of these motions here are going to be part of this 3n total degrees of freedom. So let's see how that works out here. Let's think about a linear molecule, for example, of HCN. If I look at the total degrees of freedom, 3 times 3, well, that is 9. Well, we know there are 3 translational degrees of freedom, and this is a linear molecule, so we saw it had 2 rotations, which means here we have a total of 5 degrees of freedom, meaning there has to be 4 more degrees of freedom, which can only be described as vibrational modes. Pretty cool. On the other hand, if we have a molecule that is nonlinear, like, for example, water. So here's another triatomic system. Water, we find out, again, 3n is 9. There are now 3 translational modes, just like we had, but now there are 3 different rotations that we could have. And this is just thinking about the Cartesian axis set for water. I could have a rotation around that axis, or this axis. All 3 of those would be unique. But now I have a total of 6 degrees of freedom between my translations and my rotations, which means I only have 3 vibrational modes that I would see. So this is going to be the clear thing that we'll have to remember for assigning molecules vibrational modes. If it is a linear, we're going to see a 3n minus 5 number of vibrations, whereas if it is nonlinear, 3n minus 6 is how we would describe how many vibrations we have. Now, just like we saw with the orbitals, there is a symmetry for each of the vibration. There will be a representation that is going to be analogous for each of these representations of vibrations. How do we do that? First, we'll assign x, y, z coordinates to each atoms again. Thing that's a little bit more tricky now is we're going to have to see how each axis transform with each symmetry operation in the group. And this was for every atom. So if an atom moves, we're going to count that as 0 because now it's not in the same place. It doesn't count towards the symmetry operation. If the atom is stationary and the axis direction is unchanged, it gets a positive 1 because it's symmetric with respect to that permutation. Whereas if the atom is stationary and the axis direction is reversed, it gets a -1. Okay? These are just some rules we're going to follow. We'll see an example of this here in a second. Finally, we'll sum the characters of each class to determine what our overall reducible representation is for the vibrations. Okay? So again, these are rules. Let's see how they apply. So let's come back to our good friend water, reminding ourselves this is a C2V point group, and we're going to look at the symmetry of the vibrational modes of this molecule. So, just like Lee said, we're going to assign Cartesian axes to all of our atoms. So I have a set here, I have a set here, and a set here. So 3 different coordinate axes that I have on these atoms. So we're going to start and look to see what happens to our axes upon the identity element. Identity, nothing changes, so there are no axes changes. So if I look around here, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 axes, 9, and each of them is staying the same, so it's going to be a 1. So this is a total of 9 that I would have for my representation from E. Let's look now at a C2 rotation. So remember, that's our C2 rotation, and we'll notice that our H atoms are going to move, physically move out of position. So we're not going to care about what they are. Since they both move, all of those axes get zeroed out. The oxygen, on the other hand, if we look at it, let me clear this up a little bit here, we see that the z-axis is going to stay the same upon that rotation. The y is now going to point in this direction. The x is going to point in that direction. So in other words, one axis stays the same. There's my positive 1. One axis, the x changes, the y changes. So I've got 1 minus 1 minus 1 plus 0. That is a total of a -1. On to the sigma v for the xz plane. So this is the plane of the molecule. So we see no movement of our atoms, so we have to look at every axis. And in each one, though, they all have the same properties. So for example, the z and the x are going to remain unchanged. So I've got 2 axes that remain unchanged on 3 atoms. There's 6. And if I look around here now, the y-axis does change direction on all 3. So I've got 3 times minus 1. We'll add those together. So I've got 6 minus 3. This gives a character of 3. So I've got 9, negative 1, positive 3. And we could do this with the other sigma v as well. And what we'd find out is we'd get a 1, a 0, a 0, which gives us a total of 1. So this table down here is just another way to represent the same things that I'm showing up here, but for now, all of everything here. So now what we'd see here is we've looked at all the 3n coordinates of our system. So our representation, which I'm going to call gamma, for our molecule is going to be 9, negative 1, 3, 1. Okay? We're going to use that here in a minute because this is now a reducible representation. It's not made up of irreducible pieces. We've done this before, and now we just need to reduce this to find out what all the components are. Reducing a representation to its irreducible components looks a little bit more complicated than it is. So, if we want to find out the number of irreducible representations that we have for a particular symmetry label, for example, A1, we have an equation, 1 over h times the sum of the number of operations in each class times the character of the representation times the character of the irreducible representation. So when we think about this, we should think h is our group number. So in the case of C2V, we said it had an order of 4. So let's see how this math actually works out when we put all of it together. All right, so here I have my character table for C2V, and here I have my reducible representation that I worked out on the previous page. When we look at this, we have, again, h of 4, and the number of operations in each class, well, there's just a 1 here, 1, 1, 1. So in other words, there's 1 operation per class. All right, so let's work out the math. If I want to know how many A1 irreducible representations make up those 3n degrees of freedom, I would have 1 divided by the order, so 1 over 4, times now the number of operations in a class, and we saw that was 1. We need to know now the character of the reducible representation. Well, that we said was 9. That goes there. And then we are going to multiply that by the character from the irreducible representation, and we're going to start with E, which is 1. So here's E. This one is for C2, sigma V of the XZ, and then sigma V of the YZ. So take a minute, pause it here, and see if you can make sure you understand where all of these numbers come from. Once we have all that together, we do the math and we say that, hey, we have 3 is our final result here. So that tells us in this molecule, H2O in the C2V point group, we would have 3 A1 symmetry degrees of freedom. We do the same thing to find out how many A2 symmetry irreducible representations we have. So again, I have got the number of operations in each class, which is 1. I would have the character from the reducible representation, which is here. And finally, I have the character from the character table. Now we're this character, looking at E for our A2. So again, here's E, here's C2, sigma V, and sigma V prime. Do our math here. We can find out that it's A2 equals 1. So in other words, there is 1 A1 degree of freedom in this molecule. Definitely take a moment, do the math for yourself here so that you could prove out the final two to see that we have 3 B1s and 2 B2s for our molecule here. Definitely do that in your own time. Make sure you see where these come from. This can be a real pain the first time you do it, but then it just becomes like, oh, I know how to apply the equation. So here I'm just removing all the math here and saying, hey, we found out the number of A1 irreducible representations was 3, 1 A2, 3 B1s, and 2 B2s. So in other words, our reducible representation is given as the sum of 3A1s plus A2 plus 3B1s plus 2B2s. So in other words, our reducible representation is just the sum of all of the irreducible representations that make it up. That's all we're doing here, decomposing it into its primitive components. All right, so what does all this mean? How does this connect back to what types of motions we have and what the symmetry of those motions are? So again, here is that decomposition that we just did on the previous slide, and here is my wonderful character table. So if we want to find out what the vibration symmetry is, we need to look at everything, because remember what we've done here, this is for my total 3n degrees of freedom. This is not just for the vibrations. So what should we do? First and foremost, let's remove the motions that are described translational degrees of freedom. The translational degrees of freedom are shown here in green, indicated by the x, y, and z. So the p orbitals transfer in the same symmetry as the Cartesian axes do, which is a really interesting piece of information here. But what that means is if I look at how a z translation looks, for example, it would be an A1 symmetric mode. In other words, by translating it along the z-axis, no matter how I do that, that would have an A1 irreducible representation. Next, we can remove the rotational degrees of freedom. That's what these capital R's here are telling us about. So if I look here, I've got one that's an A2, that's the RZ, one B1, which is RY, and one B2, which is the RX. So I want to remove these 6 degrees of freedom from my reducible representation, because this is the translations and the rotations. We want to know about vibrations. So let's subtract those out. So when I do that, that's all I'm doing here. So I've got my reducible representation here, my translational degrees of freedom here, my rotational degrees of freedom here. And we're just going to treat this like an algebraic problem at this point, do the subtraction. And what we're left with is that our vibrational representation is 2A1 plus B1. So we have 2 vibrations that have A1 symmetry, one that has B1 symmetry is the way we would look at this. All right, I think that's probably a good place to cut this one off. We're getting a little bit long-winded. We'll see some more examples of this in a while and see what does this actually mean when we put it into practice. What does an A1 vibration mean? What does a B1 vibration mean? We'll see that in another video. So, as usual, we'll talk about this in class. If you have questions, let me know. And as always, be excellent to each other.